the moment, let's continue with our kind of basic things as far as matrices are concerned. Now we know how to multiply, we know how to add matrices. That's right. Now, for this, I would like to discuss with you some special types of matrices. For example, in matrices of order 2 by 2, square matrices, we've got a matrix like this. I'll name it Z for a reason. 0, 0, 0, 0. We call that a zero matrix. Zero matrix. It can even be another order, but when it's got all the entries being zero, we just call it a zero matrix. I hope you see that when you add this matrix or you subtract from any other matrix, it just behaves like zero with numbers. 2 plus 0 will be equal to 0 plus 2, and that is going to be equal to 2. All together. Good. Then another matrix which is special, which we want to talk about, I think, because we want to talk about something special, again, is a diagonal matrix. Like we've got the number 4 here, 5, 6, 0, 0, 0, 0, 0, 0. These entries there along that line, we call that diagonal of the matrix. Like we have got a diagonal of a rectangle, we call that a diagonal. Now this is going to be called the diagonal matrix. Why? Because it's got non-zero entries only along the principal diagonal. I said entries. I hope I remind you that these numbers here are called entries of matrix or elements of matrix. All together. Okay. Then we also got triangular matrix. When we've got something like this, we'll come back to diagonal now, but I want to finish up this. Triangular matrix, something to look like this. We've got 1, maybe 2 there, 3, 4, 5, and the 6. Then 0, 0, 0. Now, we've got our principal diagonal there. We call this our principal diagonal. And then this becomes our secondary diagonal. All together. So, below our principal diagonal, we've got all zeros. Then we call this a triangular matrix. Triangular. Like a triangle. Triangular matrix. All together. And this one precisely, we'll call it an upper triangular matrix. Then you can think of what will be lower triangular yourselves. All together. So I'll leave those gaps, you must fill in the gaps. The same way, like when you're looking at generations, you don't see everything, you fill in the gaps. All together. Okay. So then, proceeding with that, then we've got a special diagonal matrix. Let's talk about it in the 3 by 3 matrices. This one. 1, 0, 0. 0, 1, 0. Not this is a diagonal matrix like that one, but it's a special one. 0, 0, 0. Why do I say special? Because it's a diagonal matrix. Along the principal diagonal, we've got only one type of entry, and it's a special number, 1. And remember, 1 times A is equals to A times 1 is equals to A. All together. And then we say A1 is an identity for multiplication when we're dealing with what? Real numbers. We multiply any real number by 1, you leave it as it is, identical as it is. So we call it an identity. So this one, we're going to actually call it an identity matrix. Identity matrix. We're not calling identity matrix because it's made of ones, though. Because it multiplies any matrix which it can multiply and they leave it as it is. If you now you can take this matrix T, you multiply T by I3. If you multiply 3 by I3, just check. If I take this column and make it horizontal there, it's going to multiply 0 there, 0 there, and 1 there. So the answer there will be 1, isn't it? Then I come here. What's going to happen? I'm going to multiply by 1 there. I'm taking this column. I'm going to multiply by 1 there, and 0 there, and 0 there. So that will be 0. When it comes down here, it will be 1 there, by 0 there, by 0 there, to be 0. So you see that column which is there is been left as it is. So we come to this one, we multiply by this one. When you come this way, multiply. 0 is going to multiply here and 0 is going to multiply there. So all this 0 is going to run through there and they run through there. So I'm going to have 1 at the center here, which is going to give me 2, 4, and 0. So far that matrix is still the same, isn't it? Then you come and multiply with this one. These zeros are going to lie here, 0, 0, 1. So all these are going to be 0, 0. Then this one will multiply all these entries, and the remainers there should be 3, 5, and 6. So because of that, and this actually is going to be commutative, it's still going to be equals to I3 multiplied by T. So whichever way you do the multiplication with an identity, you'll still get the same, the same matrix altogether. That is if both can be, if the both multiplication can be done. Are we there? Good. So now it sounds going to be interesting very soon. Check now. We've got a matrix which you call I3. You must know that this I3 belongs to the set of matrices of order 3. I'm going to use that symbol there to signify the collection of all the matrices of order 3. And then this is the identity. So any matrix which is here multiplied by that will remain as it is. Altogether. So when we look at I2, we're looking at an identity of the collection of all matrices of order 2. Now it's 2 by 2. Altogether. Square matrices in this case. I'm talking about square matrices. Are we there? Okay. So now to get this thing, what do we know here? We know that A multiplied by the identity is equals to identity multiplied by A is equals to identity. Sorry, it's equal to A. Sorry, not identity. It's equal to A. Now, we know again in numbers A times 1 is equals to 1 times at and equals to A. But we know also with numbers that if we've got A not equals to 0, we can produce this one by saying A multiplied by A to the power minus 1, which is the same thing as A over 1 multiplied by 1 over A altogether. And that will give us 1. Check what I've done here. I've written the A to the power minus 1. I don't have something like this in matrices, 1 over matrix, but I have something like this. In other words, now the question is there a matrix which I can get which is A power minus 1 multiplied by A exactly like I've got here, in such that I will get the identity in a similar way and multiply A post multiplied by the same kind of matrix we call this mutation and they get the identity. The question is does this happen with matrices? Does this happen with matrices? The answer is a big yes, but under certain conditions. I'm not going to talk about the conditions now, but I'm just going to think that we're going to work with this and see what kind of a matrix is that. We're going to start small, start by 2 by 2, and see what happens. Altogether. Okay, let's go this way. Let's say we've got a matrix A here. The entries of this matrix are A, B, C, D. Listen guys, when I'm putting letters like that, I don't care what number that number is or what sign that number is called. I'm just taking numbers in general. Altogether. I think you should have learned that so far at school. You should have learned by now that when you take letters, we're representing numbers in general. We're just not talking about a particular number like 2, like 3, like 4. We're talking about numbers in general. Altogether. So we're talking about the matrix which is made up of numbers like this. There could be fractions, there could be whatever type of numbers. So then we're checking whether there is another matrix which is A that. And then we don't know how those matrices, those entries of that matrices look like. So what I'm going to do, I'm going to say X, Y, U, V. So now the question is there, if we got A plus A, which is called this matrix, is there any other matrix like this such that when I get this multiplied, I get an identity? For you so far is a question. All together. You must be curious now. You must be like getting anxious. Is this possible? How this thing going to look like in terms of this one? All together. That is the thing. If you don't have an excitement, then you are immune to excitement, then it's a problem. Okay, so let's see. Let's do this. What do we know this? Yes, we know this. This is 1, 0, 0, 1. All together. Okay. Let's suppose we knew this matrix, we're wondering what this is. All together. So if we knew this matrix, we're wondering what this is. In this case, we're going to search for X. We're going to search for Y. We're going to ask ourselves, how does U look like? And ask ourselves, how does V look like? All together. Okay, so what do we do now? Let's do exactly this. Let's do exactly what this thing is saying. It's saying A, B, C, D. Beautiful. And then here, it's saying X, Y, U, V. Equals 2 by 2 multiplying 2 by 2, result 2 by 2. All together. Then 1, 0, 0, 1. Multiply matrices, we know now how to multiply matrices. So it's going to be AX, X is unknown, plus BY, Y is unknown. Then CX plus DY. Then here, AU, U is unknown, plus B, V, then CU plus DV equals 1, 0, 0, 1. Beautiful. What does that mean? What does this mean? It means that these matrices are equal, isn't it? But we said when we say matrices are equal like this, we simply mean that AX plus BY is equal to what? Equal to what? 1. That is the equality of matrices, isn't it? Then we mean CX plus DY equals to 0. That's the equality of matrices. This is a system of equation. Equation 1, equation 2. Unknowns X and Y. Do you agree? Okay. Come here. This one should mean AU plus BV equals to 0. Here, CU plus DV equals to 1. Equation 1, equation 2. Unknowns U and V. That's what we said we were looking for there. All together. We said we are looking for U and V. Unknowns here, U and V. Unknowns U, X and Y. So let's take these things one by one and solve them. Let's solve for X, solve for Y. I'm going to use a simple method which you know from school, which is method of elimination. I will draw a line there and draw a line there and say, I want to eliminate X in this equation and then solve for Y. All together? Okay. So I'm going to multiply this one by C and multiply this one by minus A. Here I'm going to have AC and here I'm going to have minus AC. When I add the two of them, check what I'm going to get. When I add the two of these things, I'm going to have 0 there. Then there, I'm going to have BC. Do you agree? I'm multiplying by C. I'm going to have BC minus AD. Do you agree with me? Do you agree with me? So I'm going to write there BC minus AD. In brackets, all those, they've got a common factor Y. Please agree. If you don't agree, tell me if you don't agree. Is anyone is feeling some stomach ache? No. Okay. When I get to this side, I'll multiply this by C and this one by minus A. But this will be 0. Then I'm left with the C only. So I've got C there. What does this tell me? This tells me that Y is equals to C over B C minus A D. Can you please write that down? Please, everybody write that down. Write that down so when I get to a fresh page, you can easily give me the values next or easily. Okay, let's now get to the next question now. Next question, I'm going to eliminate Y because I already know Y. I'm going to eliminate Y and solve for X. Check what I'm going to do here. I'm going to multiply by D here and multiply by minus B here. That's just a choice. I'm going to multiply by minus D there by B. Just as a choice. Altogether. So I'm going to have here. I'm going to have BD here and minus BD here. I add the two. I get 0. But when I come here, I'm going to have AD here minus BC. AB minus BC. I always advise you that when you're multiplying, dealing with letters, when you're multiplying, put your letters in alphabetic order. You'll easily see the common factors altogether. So now here, this will be C. This will be X. Equals to, when I multiply this right hand side, I'll multiply this one by D and this one by minus B. That's a 0. That remains as a D. What does this tell me? It's telling me that X is equals to, I'm dividing both sides by, remember this is the equation 2x equals to 8 altogether. This equation is exactly of this nature altogether. So I'm dividing both sides by 2, or I'm dividing both sides by this number here. So I'll get the D over A, come again? Here AD, okay, AD minus BC. So there's a misprint here, isn't it? Okay. So that's that. Altogether. But let me tell you something. I see something very funny here. I've got AD here, I've got BC, I've got PD there. But I don't like this one. Because it doesn't start with the A. My alphabet starts with the A. How can I write this thing in such a way that it starts with AD? Take out the common factor minus, isn't it? And then take the minus sign to C. Then I've got A, D, minus B, C. And then it looks beautiful. Then it looks beautiful. Why is it beautiful? These numbers, these X and Y have got a common denominator. Then to me it looks beautiful. All together? Okay. Now let's come to the next one. The next story is about this. Let's write there. AU plus BV equals to 0. CU plus what? DV equals to 1. I draw again my cross. This is equation 1, this is equation 2. Altogether, I want to eliminate U first. It's up to you what you want to eliminate. You can start with V, or I want to eliminate U first. What I'm going to do, I'm going to multiply here by C, or let's say by minus C there, and by A there. Then I've got minus AC minus AC, 0. I've got a 0 there. Then here, I've got minus BC minus BC. Is it a coincidence? Suspicious. Then plus AD. This is exactly that. But let's not hurry. And this is V. Equals minus C there, multiply, I get a 0. There I get A. Then I get that V is actually equals to A over AD minus BC. You see? It's beautiful, eh? It looks beautiful to me. Yeah, beautiful to me. Feels very, very beautiful. Let's move on. Now let's eliminate V. What are we going to do here? We're going to multiply here by minus D. Let's Let's multiply it by D and multiply it by minus B. If I do that, am I right? I'm eliminating V, yes. I'll go to this eliminated. Here, then here, I'm going to have AD minus BC with a U. Do you agree with that, everybody? Okay, equals. This minus D plus D multiply this 0 is 0. Then this minus B is there. I get that. Then I get here that what? U is equal to minus what? B over AD minus BC. We've got a common denominator everywhere. And then this starts to be beautiful. What can we do now? We are now going to write our A as we were given. Remember how A was given. Do you remember A? Do you remember A? A is here. A, B, C, D. And then we're going to write our A power minus 1 the way these things here are saying. It was X, Y, U, V. All together. I'm reading the column. X, Y, U, V. You have that in your paper, eh? Then let's write that on a new page here. Let's have A. A is equals to A, B, C, D. Sorry. Our A, power that, we have now identified it. It's not anything very funny. It's something which has got things which you have seen before. What is X? We've got it. I said copy it. You didn't copy X. D over AD minus BC. And Y? Minus C over AD minus BC. And then U minus B over AD minus BC. If I were you, I would just say over the common denominator. And then V over the common denominator. What is this now? A over the common denominator. Some people don't know how to speak. Now, let's do this. Remember we said you can multiply what? You can multiply matrices by numbers, isn't it? You just get into the matrix and multiply everything by number. Altogether. Now here, the number we can seeing here, I'm seeing a number 1 over AD minus BC. That is a number only when AD minus BC is not equals to 0. Altogether. So already I'm saying for this matrix to exist or to make sense, AD minus BC must be different from 0. I said that. I said under certain conditions. That's what I'm about. That's one of the conditions. This matrix will be there only when AD minus BC is not equal to 0. And then this will look like 1 over AD minus BC multiplied by D minus B minus C and A. And this matrix, we're going to call it the inverse of A. I'm giving you as a task your homework. Go and multiply these two matrices and make sure that you get the identity. All together. Let's give names to special things here. Let's give names to special things here. Let's give names to special things. Let's give names to special things. What has really happened here? We've got a special something called the AD minus BC. We can compare it with this matrix A, B, C, D. But if we want them equal like that, this is not a matrix number, is it? Then we're going to call this, put something like this, to indicate that we're not talking about the matrix but by a number and this number. Look, I'm saying I'm comparing this number with the matrix I was given. I wrote it there. But now I'm not putting brackets there. I'm putting straight lines. Those straight lines, they tell you something. They're giving a name to this number. What name are they giving it? They say, these straight lines are saying determinant of A. Where is A? A is something like that. So now it tells you that the determinant is a number, but how do you get that number from this matrix? You multiply the principal diagonal. You subtract the product which you get from the secondary diagonal. That is called calculating a determinant of a 2 by 2 matrix. If I were you, I would write it in capital letters because this we're going to say it several times. That is calculating a determinant using calculating a determinant of a 2 by 2 matrix. That is going to teach us how to calculate the determinant of 3 by 3 matrix. And that we are going to extend it to calculating a determinant of a 4 by 4 matrix. That will extend to our imagination, extend that to how we could multiply and get a determinant of a 100 by 100 matrix. That's just an extension and extension and extension of a small thing, you know. So guys, we've learned a new word today. What is it called? Determinant of a matrix. It's a number. It can be 0, it cannot be 0. But the inverse will exist only when the determinant is not equal to 0. All right there. A inverse exists. And in this case for 2 by 2, we know how it looks like. Exists only when the determinant, which also can denote this way, with a bar like that, like absolute value, or with a function like this, dit of A. This is actually a function. In other words, to a matrix, it assigns a number and the only one number. Altogether, it's a function. Determinant is a function. It's defined, the domain is square matrices, and it gives you a real number. That's what this is saying. Call that a determinant. So this guy called inverse of matrix exists only when the determinant of that same matrix is not equal to 0. Are you happy? Are you happy with that? Good. Then immediately I can come up here and say, okay, here is a matrix. A equals to 1, 2, 3, 4. Find or determine the inverse of this. Guys, this is very simple. Just check. Look at this. I'll come and look at this. And look at this. And check what has happened here. What has really happened here? Something very, very mechanical. The only thing I need to calculate is the determinant. The rest is mechanical. What do? I swapped around D and A. Altogether. Then immediately I multiplied this diagonal by minus. That's all what you need. According to this is mechanical. You get A there. What is one thing shown there? What A inverse is? It's just saying exchange A and the D. And then multiply this by minus 1. Altogether. Good, man. Then do it for this one. Give me the inverse very fast. I will start by breaking the brackets and do the easy things. And tell. But first of all, you mustn't do this first. The first thing you must do, you must check whether it exists. Because you must be trying to do something that does not exist. What is the check? Check the determinant. What is that? 4 times 1 minus 2 times 3, which is equal to 4 minus 6, which is equal to minus 2, not equals to 0. Therefore, A inverse exists. That exists. All together. Then I'm going to do that. I can now go and play. I already know the determinant. I can just say minus 1 over 2. Then you fill in the gap there. All together. Quick, quick. For this one, it's quick, quick. Doesn't it look beautiful? Okay, what's coming here? It's going to be minus 2, minus 3, 4, and 1. Let's multiply these two. It will be multiplying. Minus half can remain outside there. And you multiply there. 4 minus 2 minus 3, 1. Then multiply by 1, 2, 3, 4. This we're going to do at the end, altogether. First of all, let's multiply the matrices. So we're going to have half here, minus half. And then we go there. This is going to multiply there. This is going to multiply there. Could be 1 times 4 minus 6. What is that? Minus 2, isn't it? Then when you come down here, this is going to be minus 3 plus 3, 0. When you come with this one, it will be 8 minus 8, 0. When you come here, it will be minus 6 plus 4 minus 2. Kick this thing into the matrix. Minus will say minus. Normally, this is what happens. If a minus, see this minus coming together. This one kicks this one here. Then it goes like this. Then this one jumps over. You didn't see that, no? This minus mixed this one. This one will kick this one right here. And then it goes standing up. Then it jumps over. Then they stay like that. So if that happens here, this minus will kick this minus. We're going to be left with a 2 over 2. What is a 2 over 2? It's a 1. There, it's a 0. There, it's a 0. Same thing happens there. It's a 1. You guys, don't you see that is beautiful? That's it. There's attended. How do you know, guys? There is how beautiful the thing is. That is called an inverse of matrix. Now, let me tell you something now. I said we're never going to talk about multiplying, dividing matrices. But when we're talking about numbers, we write 2 to the power 1 multiplied by 8. And they say that is 8 divided by 2. Altogether, we're not going to have something like 1 over a matrix A like that. We're never going to do this. This is capital nonsense. I said capital nonsense. So now, if we were to mimic this, we would say our division of matrices, we're going to replace it by multiplying by an inverse. Because even with numbers, division is multiplying by an inverse. Altogether. So we're not going to talk about what division of matrices. We're going to talk about multiplying by inverse. Isn't that beautiful? It's beautiful. We've had addition, multiplication of matrices. We don't have division. We replace it by multiplying by inverse. Then we've got all our operations. Addition, subtraction, division, which is said in another way different, and the whole setup things happen. And whenever we're talking about inverse of matrices, we're talking about square matrices. Now we'll be talking about these sets of matrices like this. Matrices of order n. 2 by 2, 3 by 3, 4 by 4, and so on. How do you do that, guys? Okay. This looks beautiful to me, man. This is really beautiful to me. So what can you do now? You can now go and practice multiplying matrices, adding matrices, calculating determinants, finding inverses, and so on and so forth. Otherwise, at that point, let's conclude by saying thank you for listening.